Yes, done.
Okay, thank you. Okay, it's a pleasure to introduce the Professora Érica Boizan Batista from Universidade Federal do Cariri. And today she speaks about combinatorial models and the topological classification of finitely determined map germs. I would like to say thank you very much, Érica, for accepting this invitation. And then you may start when you are ready. Thank you.
Hello, thank you, Rodrigo. Well, first, I would like to thank the organizers for inviting me and also for adjusting to my schedule. Usually I have classes on Tuesdays morning, but today was an exception and they kindly accommodated me. So thank you very much. Well, let's see how I do it. I already with the presentation. Let me see. It's okay? Everyone can see it?
Yes, right.
All right. So, well, as kindly introduced by Rodrigo, I will talk a little about combinatorial models in topological classification of finite determinate map germs. Well, in 1964, Hanneton showed that the topological classification of finitely determinate map germs from Rn to Rp is discrete, and hence there are no moduli. Since the classification of the topological problem is discrete, it is a natural open question to find a good combinatorial model which codifies the topological information of this map germ. Well, associated to it, we have also a very important result with Fukuda, which tells us about the topological structure of finitely determined map germs. Here we denote by S tilde the inverse mate of the S, the surface SP minus 1, that is the sphere, and also by D tilde, the inverse mate of the disk, okay? As defined here, okay? So the Fukuda's theorem says that if F from Rn to Rp is a finitely determined map germ, then up to A equivalence, there is a representative F and epsilon0 greater than 0, such that we have the following properties. Here we divide it in two cases. First case is when we have the zero set just 0. This is a case that will happen when we have the dimensions n equals to p and p greater than n. Well, mostly, right? So if the zero set is just 0, there is epsilon 0 greater than 0, such that for n number epsilon, with epsilon between 0 and epsilon 0, we have three properties. The set S tilde, that's the inverse mate of the sphere, is a submanifold without boundary, which is diffeomorphic to the standard unit sphere. Also, the restrictive mapping to this set, the S tilde, is topologically stable. And the restrictive mapping to the disk is topologically equivalent to the cone of the first restriction here. That means that we can use the first restriction to the S tilde as an invariant to classify our germ. In the case B, we consider the case when the zero set is different of 0. In this case, for any sufficiently small positive numbers, epsilon and delta, where the upper bound of epsilon depending on F and the upper bound of delta depending of epsilon and F, that will be epsilon 0 and delta 0. We have that the zero set enter the sphere is diffeomorphic to the zero set enter the sphere for the radius epsilon 0. Here, epsilon is between epsilon 0 and 0. Also, the intersection of the disk with radius epsilon with the inverse image of the, sorry, here I put the, would be p minus 1 here. Well, with the inverse image of the sphere is a manifold in general with boundary, and it is diffeomorphic to the disk minus the inverse image of the sphere. Well, also the restriction to the set is a topologically stable map, and its topological class is independent of epsilon and delta. We can see here that these two cases have properties similar properties, but there is no equivalent statement in this case as in A3. Not sure if my English is okay, but I mean, we doesn't have a statement that says that we can use the restriction F to D and inter S tilde here as an invariant. Okay, so to complete this case, to complete this part of the theorem, well, this is an example what will happen, the situation, right? We have a result that help us to complete and use and make the situation such that we can use this restriction as an invariant. This part of Cood's theorem says that we have the restriction and the domain of this restriction like this, a surface with boundary, right? So then for completing the part B of Fukuda's theorem, we have this theorem due to Costa, Non Ballesteros, and Reeb that says that if we have F from Rn to Rp, finitely determined, not germs, such that the zero set is not just zero. This case will happen when we have n greater than p. Okay, for its epsilon greater than delta, and they both will be positive, small enough, there exists a continuous and surjective map R from n epsilon delta. That will be this surface here. And V epsilon, that will be the intersection of the zero set with the disk. But that the link diagram is independent of epsilon and delta. So it preserves its topology, right? So then the restriction, the link diagram is independent of epsilon delta, and the restriction F to this, the disk inter the inverse image of the disk is topologically equivalent to generalized cone. Okay, so this theorem will be working for us as this third part of the case A. And because of it, we will be considering the link of germ. So, assuming F, a finitely determinate map germ, we can apply the Fukuda's theorem to obtain a representative F satisfying A or B, depending on the zero set. And we define F, we define gamma F as the restriction of F to the disk inter the inverse image of the sphere. Okay? And we call it the link of F, where F is a representative that satisfies Fukuda's condition. Well, as a corollary, let F and G be two finite determinate map germs. If gamma F and gamma G, their links, are C0A equivalent or topologically equivalent, then F and G are C0A equivalent. Here, this shows that we can then use gamma F, the link, right, as an invariant. So with this situation then, and considering the first statement, the first commenter about the combinatorial, the interesting of finding a combinatorial model, we have some questions presented by Nuno Ballesteros that we will record here. Well, these were made, let me see, 10 years ago, something like this. Maybe more. So these open questions were presented by Nuno Ballesteros, São Carlos, I believe. And, well, the first one, considering all we have talked about, find a good combinatorial model which codifies all the topological information of a stable mapping gamma from Sn-1 to Sp-1. And hence of the germ, because the link, right, here the gamma will be the link, okay? This is why it's using Sn-1 to Sp-1. But here you can see that he's not considering cases with boundary, right, in the domain. This is because we didn't have that theorem in this situation when he presented these questions. Also, determine the stable maps gamma from Sn-1 to Sp-1, which can be realized as the link of a finitely determinate map germ F with the zero set just zero. Here again, he didn't consider the case when we had the zero set, not just the zero, but the question for that case will be the same, right? Determine if the link is a complete invariant for finite determinate map germs up to C0A equivalent. Find relations between analytic invariants of F and the topological invariants of the link, and study the topological transitions in one-parameter families of finitely determinate map germs. In particular, study the topological triviality of the family. Well, in this talk we will not sure if that will be the word, and we will talk more about this first question and the fourth question, okay? So, we can, when we talk about this problem, the topological classification, we can think about the dimensions and divide it in three cases. When n is equal p, when n is greater than p, and when p is greater than n, right? Some combinatorial models were proposed by Nuno Ballesteros and his collaborators. And for here, I will be talking about the special case when n or p is equal to 2 or 3, okay? For the case when we have finitely determinate map germs from R2 to R3, they use the doodle. When we have map germs from R2 to R2 or from R3 to R3, they use Gauss words or Gauss paragraphs too. Here. And for the case when we have n equal to 3 and p equal to the Reeb graphs. We will be talking about this specific case here, the Reeb graphs, as a way to exemplify the situation. for combinatorial models. Also because the Reeb graphs, this case when R3 and R2 is interesting because it will have cases in the first part when the zero set is just zero, and also when the zero set is not just zero. We have classes in both. So the Reeb graph was introduced by Reeb, and it's well-known completing topological invariant for Morse functions from N to R, where N is a connected surface. So we have this definition, the Reeb graph of a stable function f from N to R is on a connected surface. N is the space whose points are the connected components of the level curves. And this space is a finite complex. Well, we will be studying the case n equal 3 and p equal 2. In this case, we will have a graph specifically. But we can also have a more generalized case when we have greater dimensions, okay? When n is equal S2, the Reeb graphs associated to a Morse function from S2 to R is a 3. Here we have an example, sorry, just a moment. Here we have a very simple case when we have here a function, high function, right? And for value 1, we have boundary, okay? We are considering also when we have possibility of boundaries. And for this case, the value 1 gives us a curve here. Here in this, can you see my, how the name of this little hand here? Can you see when I point things on my presentation?
Yes, yes.
Yes, we can see.
Okay. Thank you.
It's possible to see, yes.
Okay, so for value 1, we have this curve that is a boundary, right? And we denote it by a white vertex. And for saddles and maximals or minimals, we have black vertices. For maximals or minimals, we have black vertex with degree 1, and for saddles, degree 3. In this case, okay, it's a case when we are considering that the boundary is all given by one level curve. All right. So then we define the following. Two Reeb graphs are equivalent if there exists abstraction phi from V to V that preserves order, and abstraction C from E to E, such that here V is the set of vertices and E is the set of edges, okay? And these two projections have to satisfy this equality. Okay. Also, we have a theorem due to Reeb and Arnold. Let gamma and delta from N to R be two stable functions, where N is a closed connected surface. Then gamma and delta are topologically equivalent if and only if their Reeb graphs are equivalent. Here you can see that also this result is for closed connected surface, not considering at first the case when we have boundary, right? So it was necessary to study a little more the Reeb graph and show that it's also a topological invariant for the case when we have the surface with boundaries. So we could use it as an invariant for the links in the case when the zero set is parent of 0. It's not just 0. Then we define the generalized Reeb graph. So since we want to classify the links of germs, we need to consider Reeb graphs of stable maps from n equal to S2 minus 2L disks. Why would it be 2L, right? So not S2 minus L disks, right? It's because we are working with finitely determinate map germs. So the zero set, let's just go back here a little so I can show you. The zero set will be able to count, let's say, the boundaries, the connect component of the boundary of the surface, right? And for finitely determinate map germs, in our case from R3 to R2, we have that the zero set has always even number of half branches. Okay, so let's go back. Okay. So also we are considering that our maps are going to S1. What's a little different of our result here, where Reeb and Arnold were considering R. Okay, so for this we use the same equivalence relation. Okay, so we take all the level curves and contract it to a point. All the connect component of level curves and contract it to points. Okay, and you also get a graph as a result. But now each connected component of critical level curves will be also contracted to a vertex. Before we had that only the connect component of level curves that had critical points would give us vertices. But now also the connect components that have only regular points will also give us vertices. This is because we are considering maps that goes to S1. And we need to count how many times we will I don't know, make the way, right? And go around the S1. I hope I'm making me understandable. Anyway, so this is why we have these little chunks here, but also because we have a special situation and we are considering stable maps. We do it to result to from Sayaki. We have that the curves that the level curves that intercept the boundary will be transversal. Because of it, we have more topological types for the level curves. Okay, we will have circles, saddles, maximal minimals. You see, for the first example, we had just this first three one. Now but now from now on we have also lines, half open saddles, and open saddles. Okay, this will be our level curves from now on. So each edge of our new graph now will be of two types. First, in the first example here, we have just edges that were given by level curves that were circles, right? Now we have another possibility. So we denote the edges depending on their kind of level curves. For circles, we have a thin line for the edge. And for lines, we have a bold one. Okay. Each vertex of the graph can be of 7 types, okay, corresponding to regular connected components, to maximal minimal critical points, to saddle points, to half open saddle points, or to open saddle points, or corresponding also to a boundary, okay? That will be a special case when we are talking about half trees. That will be a little more up on ahead. Okay. Anyway, when we have a special case like this one, we will denote the vertices with white vertices. Okay. But in general, for when we have a stable map, we will not have this. Okay, we have just black vertices, and we have all this type of vertices. So a saddle, this will have degree 3 and only edges, thin edges. Also half open saddles, maximals or minimals, minimal points. Right? Here are regular points of type circle, right? Circle type, and also regular point, regular vertices for the case when we have a line, right? Corresponding to the singular value. Here we can see that only looking into the graph we can already know which type of level curve we are talking about, because they are all different. All right, let's see. So let's V1 to VR and the critical values of gamma. We choose a base point V0 and an orientation in S1, and we can reorder the critical values such that V0 is, well, we have this order, new order, where V1 is lesser than V2, yes, a crescent one. And we label each vertex with the index I. It corresponds to where I, the vertex I, will correspond to the critical value Vi. And we define the graph given by the any with the equivalence relation, right? Together with the types of the edges and the labels of the vertices. Each is called generalized Reeb graph associated to gamma. Here are some examples. Here we took the example when we have four connected components of the boundary. And the graphs corresponding to it. Here I put just the level curves that contain critical points, okay? So here with two open saddles, two half open saddles, two open saddles. Here with two open saddles, two half open saddles, and two maximals or minimal. And here we have the corresponding Reeb graph. So, how the Reeb graph relates to the map germ, right? It's a natural question, right? What happens is that each half half branch of the singular set corresponds to a vertex of the Reeb graph of type maximal or minimal. If we are in a half branch of type finite fold, and of type saddle if we are in a half branch of type indefinite fold. We will have just two cases here because we are talking about finitely determinate map germs, so we choose epsilon small enough so that this case will be true. Okay. Each half branch of the critical set corresponds to a critical value of the link. And this value defines the label of the vertex of the Reeb graph. And the set XF, that is the closure of the inverse measure of the discriminant minus the singular set of F, is a regular surface outside the origin, okay? And some of these connected components of XF except 0 are cylinders going from the origin to the boundary of U. And this corresponds to regular vertices to the Reeb graph. So this is how the Reeb graph relates to the map germ. With these informations and with the property of the Reeb graph is a complete invariant that was proved also. And for the case when the domain is a surface with boundary for stable maps, right? We have the following theorem that F and G from Rn to R2 with finitely determinate map germ, then the following are equivalent. First, F and G are topologically equivalent. The Reeb graph of the associated link of F and G are equivalent. So, and 3, the link of F and G are topologically equivalent. So, if we want to classify the map germ, we can use the Reeb graph as complete invariant. Until now, we have talked about mostly about the first question that was made by Nuno Ballesteros, right? Now let's talk some about the first question. To exemplify then how we can relate the Reeb graph with other invariants, we will talk about the topological classification of Cohen-Kuan map germs. So now we especially consider the finitely determinate Cohen-Kuan map germs from R3 to R2 and present a topological classification for map germs with Boardman symbol sigma to 1. If F from R3 to R2 is a Cohen-Kuan map germ, then we have a representative of F that can be written as F of X epsilon Z equals to X 8X epsilon Z. Okay? So we associated to it, we can associate to it 8 plus X and 8 minus X, and that will be functions, let's say, restricted to when X is positive or X is negative, okay? And we associate to each one of these functions, these maps here, we associate to partial trees. That will be Reeb graph, but with a boundary, okay? That is similar to the one I showed before, okay? Here we have a definition that's kind of not very beautiful, but anyway, let F from R2 to R2, a finitely determinate Cohen-Kuan map germ, okay? Given this way, X, 8X epsilon z. Then we consider x0 such that the I'm not sure absolute value of x0 is between 0 and epsilon. And then we take 8 tilde x0 such that we have that x0 times delta 1 delta 2 intersect all the positive half branches. Okay, if if x is greater than 0, okay, and all the negative half branches if x is less than 0. And we define partial trees of 8x plus and 8x minus as being the Reeb graph of this of h tilde x0 and of minus 8 tilde x0. Well, it will give something like this. Okay, we have that for half of our germ, we have a partial tree that describes the topological information of this part, and for the other half, another partial tree. What we have to do is to glue this one and see if it will give us the Reeb graph, the complete Reeb graph. Also for the case when we have the zero set not just zero. This is a case when we have the zero set not just zero. So we can see that if we glue this part with this part, we have a sphere. But we have to consider also the case when we have the zero set not just zero. And this will not be so cute as this first one. It's also possible to glue these partial trees and have our complete graph. Okay? So we define how to glue it. I will not talk much about it. It's a technical part. Okay? And we glue these beautiful little parts and get a sum of partial trees. This sum of partial trees is actually equivalent to the Reeb graph. Also for the case when we have the zero set not just zero, we have the sum of partial trees that is equivalent to the complete Reeb graph. Okay, this is how we find calculate the Reeb graph for the case of rank 1. Okay. Then we have the following theorem that says that if f from R3 to R2 is a finitely determinate map germ of corank 1 given by this x 8x epsilon z, then the sum of partial trees is equivalent of the Reeb graph, as we said, of this link. Okay, so let's see the example of Boltzmann symbol sigma 2, 1. By the splitting lemma, we have a representative of f, which is given by x, 8x tilde, epsilon, y, sorry, plus minus z2, where this 8 tilde is like this. Yk, well, have this graph normal form, okay? Then to construct the partial trees of 8x plus and 8x minus, where we have these guys here, okay? We need to calculate the critical points, okay? In fact, we calculate the Jacobian and the Hessian matrices of 8x and have this. And we can see that the Hessian depends exclusively on this part here, right? This is why we can show that hence, since this partial derivative determines the signal of the determinant of the Hessian, if we fix x different of 0 and for z equals 0, we have that x y0 is a saddle point of 8 if and only if we have that this partial and is 0 and this other partial is negative, and this happens if and only if y is a maximum of 8 tilde x. So we can use 8 tilde x to determine if we have a saddle point of 8. Okay? The same is for 8 tilde, the minimum of 8 tilde x that will determine when we have maximums or minimal of h. Okay? And then we have an example how to use it associated to the Reeb graph. So let f from R3 to R2 be a finitely determinate map germ with the zero set just 0 and symbol Boardman sigma to 1 and multiplicity 6. Then we can take a representative of f in the following way. Sorry, in the following way. For this, we consider a tilde is right here, you see? Here, before Z2. Sorry. And we use a tilde x to calculate how many possibilities we have. And we have all these possibilities for the graph of it. Since we know which critical vertices correspond to saddles and which ones correspond to maximal or minimal, we can know how many partial trees are related to that case. And now we just need to make a combinatorial of these ones to know all the possibilities of Reeb graphs, okay, for f. And then we start looking for the normal forms, right? The map germs that will actually have this behavior, okay? And we found that all the possibilities were realizable because we actually found for any of them we found a map germ that realized the graph. Okay, this is a case when with the zero set is just 0. Well, following, we also can use the same strategy, the same method for the case when the zero set not just 0. And then we have also partial trees, and we glue them, we find all the possibilities and find the Reeb graphs and all the possibilities of Reeb graphs. We also were able to find, for this case, when the multiplicity, when we have zero set different, the zero set not just 0, the Boardman symbol equals sigma to 1, and multiplicity less or equal 5, we have that all the possibilities of the Reeb graph of the link of f are realized. And we had these little cutes. These ones were nicknamed as cucarachas because they actually look like them, right? The small legs and the little body. Anyway, so these are the reference, and thank you very much.